Hi everybody, and welcome to a feedback video for the Haskell MOOC. Today I want us to think about styles of programming, I suppose really programming patterns. Listen, last week in my face-to-face lecture at Glasgow University, I asked my students to fill in a post-it note. And on the post-it note, I asked them to tell me something about Haskell that confused the students. And most of them put this down. The fact that there are no loops in Haskell. The fact that you're missing a very common imperative programming pattern, micro pattern, I suppose. You know how you can do things like this in Java or C? While n is greater than 0, do something with n, maybe say answer equals answer times n, and then maybe n minus minus to reduce it. And up here we'd set n to a value, perhaps n is 10, something like that. Down there we'll print it out. Effectively this is going to compute a factorial. Shall I write that in? This is a factorial function. And you just can't do this kind of while loop construct very easily using the Haskell features that we've looked at so far. But the point is, you don't need to. There are better ways of doing this kind of iterative computation in Haskell. And let me show you, I'm sure, to be honest, you know this already, I'm really reminding you, I suppose, of how you do a factorial computation in Haskell recursively. Let's use some patterns. So we'll say fac0 equals 1, fac n equals n star fac n minus 1. Okay? How's that? Just to make it really explicit. So what we're doing here is the same computation, right? Well, as long as we somewhere say fac n, but where n is going to be 10, you see, to compute the result. We're doing the same computation, but we're doing it in a recursive style rather than an iterative style. So let's just see if we can match things up here. So I suppose this is the base case where we're going to stop. This corresponds to the base case. The base case is like the termination condition in the while loop. And then here, where we do the computation, this is like this thing here. I suppose that's the computation there, isn't it? And then where we go round the loop again, that's this bit here, that's the same as doing this recursive call here. So I hope you can see that we're doing the same calculation, but we're expressing it in Haskell in a much more functional and I hope elegant, certainly concise way than we would in a standard imperative programming language. This particular pattern here in Haskell is what Abelson and Sussman would call linear recursion. And this time we're going to do what you might perhaps call a structural recursion. So again, suppose we're going to compute a product of some integers as we did for factorial, then what we can do is write a recursive function to do that. We can say prod of the empty list is going to give us back 1, that's the unit for multiplication, and prod of a non-empty integer list is going to be x times prod xs. And what we see here is that, again, we have a base case. And again, we have a recursive case. And we are doing this recursion on the structure of the input. So every time in our input we see a cons, here's the cons here, right? Then we're going to have to do a multiplication here. And subsequently a recursion for the rest of the list. And then when we get down to the empty list, the answer is just going to be the full multiplication. So this is a structural recursion here, and you can imagine this being very similar to something like a for x in XS, perhaps in something like Java, where you might say, let's get this right now, answer star equals x. And again, this is a similar pattern, I suppose, but we're doing it now explicitly on the structure of the input data. Great. Of course, you know, and I know, there's a much easier way to use higher order functions in order to compute a product of integers in a list. So you could just say something like fold L star 1 and then the list elements. So this here is prod. Expressed in a point-free style, so the list should go there and there. That's an integer 1 there. Okay, and this is a much simpler and more concise way, and more idiomatic Haskell, I suppose, of doing the product of integers in a list. Right, there's one more example I want to show you just very quickly, and this example here is going to be a very common imperative pattern which we are going to reproduce in a functional style. Just do the rubbing out there. Great. Okay, so this is the functional program that people are very keen to write normally. Something like for I equals 0, I less than 10, I plus plus. Okay, this is C here perhaps, and then they want to say something like printf %d \n, I. And this program here is going to print out the integers 0, 1, 2, 3, all the way down to 9. Okay, we don't include 10. So people say, well, how could you write something like this in Haskell? You've got this loop over a sequence of consecutive integers, and you're doing this IO, this function each time. So I want to show you exactly how you do this in Haskell in an idiomatic style. So first of all, let's think about this sequence here, 0 to 10. So I'm going to say 0 dot dot 9. Okay, so that's 0 to 9 inclusive, just like we got down there, and this is an integer list. And now these are integers here, and I want to turn them into strings. So to do that, I would need to call show on each of these integers, right? But I don't want to show the list, I want to show each element in the list, so I want to call map. So I'm mapping show over each of the integers in the list. So this will take an int list and give me back a string list. Okay, and now I've got the string list, I want to print out each element of that string list. So to print out strings in Haskell, I use Futurelearn. That includes the new line for me as well, Futurelearn. Okay, and I want to do Futurelearn for each string in the list. So at this stage, I can actually introduce a new function here from the Haskell library. Is called map m underscore. Right, and what this does is it takes a monadic function, Futurelearn, okay, which is in the IO monad, okay, and then it maps this function over each element of a list and returns a unit in the same monad. So if I were to say $all of this in here, then effectively this one-liner here is the same as this program over here. And you understand all of it at this stage in the course, I think. So Futurelearn, let's get these types in here, takes a string and returns an IO unit. Okay, and this map show list of ints is going to give us back a list of strings. Okay, and this map m underscore is going to take a list of strings and something which transforms individual strings into unit in the IO monad, and it's going to return unit in the IO monad. So the overall type of this thing, when we call it, is just that. What I recommend you do is to check out this function here using Google, which is a very nice resource for finding out documentation and information about Haskell library calls. Okay, that's all I want to do really, just show you that standard imperative patterns and constructs can be reproduced or perhaps improved upon in a functional notation. Great. That's the end of the feedback video. Thanks very much for watching. Please do post your comments in the Futurelearn comments forums, and please do continue participating in the course. We've got 1 week to go, and I hope you'll get on fine with the last week. Thanks. Bye.